Example 6.2, a tractor pulls a sled loaded with firewood a distance of 20 meters along level ground as shown in this diagram. If we look at the forces acting on the sled, there's a weight acting down, there's a normal force acting up, there's the force the chain's applying to the sled, I'll call it F sub T for tension, and of course there's a frictional force pulling back the other way. So we're going to calculate the work done by each of these forces. And to do that we'll need a coordinate system, and we'll take the x direction as the direction of motion of the tractor as such. Given these forces, we can now draw out the free body diagram. And here's the normal force, the weight, the frictional force to the left, and the tension force of the chain. We're given the magnitude of the tension force, the magnitude of the frictional force, and the weight. And we're told that the displacement is 20 meters, and of course that's going to be along the positive x-axis. The angle that the tension makes with the positive x-axis is 36.9 degrees. We'll calculate the work done by considering the magnitude of the force applied times the magnitude of the displacement of the tractor times the cosine of the angle between those two vectors. And we notice just by inspection that the work done by the weight and the work done by the normal force has to be zero because the tractor never moves in the y direction. These two forces are always at a right angle to the motion of the tractor. The tension force, however, will give rise to work. So here's the size of the tension force, here's the magnitude of displacement and the angle between them, and the cosine of 36.9 is 0.8, and putting in the numbers I get 80 kilojoules of work. And that work is positive because the sled is moving in the direction that the chain is pulling. Now let's look at the work done by friction. Again, the magnitude of the frictional force, the displacement. Now the cosine of the angle, or the angle between the two vectors, is 180. Tractor's moving to the right, friction is pulling to the left. And whenever a force pulls in the opposite direction the object is moving, that force will give rise to negative work. And indeed, I pick up a -1 from the cosine of 180, and I get -70 kilojoules of work. The total work can be attained in approach 1 by simply adding the work done by each of these forces, as shown here, and I get 10 kilojoules. A second approach is to actually calculate the net work done, the net force in each direction. So the net force in the x direction is obtained from the components of each force in that direction. So I'm going to have an ft cosine phi for the x component of the tension force. Here's the friction force to the left. Put in the numbers and I get 500 newtons. The net force in the y direction, of course, has to be zero because there's no motion in the y direction, and there's no acceleration, so they have to sum to zero. So the total work will be equal to the scalar product of the net force into the displacement vector. The displacement vector only has an x component because the tractor only moves in the x direction, so all I need is the x component of the net force, which I calculated to be 500 newtons. And again, I get 10 kilojoules. Both methods give me the same number, and I note that in fact the total work done is not zero, it's positive. And when positive work is done on a system, that system gains energy from the work. In this case, the energy is going to be in the form of kinetic energy, so in fact the sled accelerates. And this ends example 6.2. In example 7.2, we're going to redo example 7.1, but now we're going to consider the motion of the hand as it throws the ball. Specifically, we're going to calculate the work done by the hand as it moves the ball 0.5 meters and then releases the ball at 20 meters per second straight up. And we'd like to calculate the magnitude of the force on the ball that the hand exerts and the speed of the ball at a point 15 meters above the release point. So let's look at a diagram of the motion. So the motion begins down here, and we're going to take the origin to be y2 equal to 0. So y equals 0 is at the release point. And so we move the ball up 0.5 meters, doing work on it, then release it, and then it goes to this point, which is 15 meters, And finally to go to a maximum height about right here and then start coming down. In this coordinate system, the ball's motion begins at minus 0.5 meters. This is a conservation of energy problem where in the first part of the motion I have a force other than gravity acting, and so I'm going to have to calculate the work of that, and that's going to appear in this term. I don't need to consider gravity, the work done by gravity, at any part of the motion because the effects of gravity are carried in these potential energy terms. So we can execute a solution by identifying the positions at various points in the motion. So y1 is minus 0.5 in our coordinate system. The release point is at the origin, y2 equals 0, and the position where we'd like to calculate the velocity is at 15 meters. At 1, the ball hasn't started to move, so the kinetic energy is 0, and the potential energy is just mgy1. I must be careful to put in the minus sign for that, and I get minus 0.71 joules. Likewise, I can calculate the kinetic energy at 2, and that's 29 joules, and of course there's no potential energy at position 2. In fact, after the ball leaves position 2 and heads on up, this is its total mechanical energy at all points in the motion, because there's no way for energy to get out of the system after that, since only gravity is acting on the ball. So rewriting the conservation of energy equation, I can actually solve for the work done by the hand in moving it from this position to this position. Putting in the numbers, I find that the work done is 29.7 joules. Then I can set this work equal to the force that's acting on the ball times the distance that it moves. And again, putting in the numbers and solving for F, which is the work over the distance moved, I get 59 newtons. Now for part B, I'm simply going to use the conservation of mechanical energy equation. This work of other forces has disappeared out of the equation because the only thing acting here is gravity. And now I can solve for the potential energy at 3, which is 21.3 joules, and the kinetic energy at 3, which turns out to be 7.7 joules. But that kinetic energy is 1/2 mv3 squared, and that's what I'm looking for. So I can solve for v3, and I get plus or minus 10 meters per second. The plus and minus correspond to the fact that the velocity is first up, the ball comes to maximum height, then it comes down. So there are 2 points in the motion that the ball will have 10 meters per second. One of them's up and one of them's down. Now if I evaluate the solution, I note that again, after the ball leaves y2, the total mechanical energy is always 29 joules. But in fact, at this position, the ball's about 3/4 up to its maximum height. The maximum height from the previous problem was about 20 meters. So the ball is 3/4 up, and indeed if I look at how much kinetic energy is left at this position, as it's moving up, kinetic energy is being turned into potential energy. If I just look at the percentage of kinetic energy to total energy, that's going to be about 7.7 divided by the total energy, which is 29 joules, and this is about 25%. So only about 25% of the kinetic energy is left at this point, which is what is expected. And this ends example 7.2. Example 7.4, a skateboarder starts from rest and rolls down a curved frictionless ramp as shown in this diagram. The ramp is part of a quarter circle of radius 3 meters. We'd like to calculate the speed of the skateboarder when he gets to the bottom of the ramp and also the normal force acting on him. Let's look at the forces acting on him at an arbitrary position along the ramp. And of course there's the weight, mg, which is straight down. But there's a normal force that's actually going to point towards the center of the circle. And if we now draw a free body diagram of the motion, as shown here, we see that this normal force gets greater and greater as the skateboarder gets down to the bottom of the ramp. The reason for this is that the normal force has to both cancel out some of the gravity as he gets closer to the bottom, but as the skateboarder picks up speed, I'm going to need more normal force pointing towards the center of this circle in order to get the proper centripetal acceleration to be consistent with circular motion. We also note that the normal force is always acting at a right angle to the motion. So though the force is present in the problem, it can't do any work on the skateboarder. So this suggests that we can use conservation of mechanical energy. In other words, the work done by other forces, and there's only one other force, the normal force, is zero. So we'll begin by writing down the kinetic and potential energies at the 2 points of interest in the problem. The initial position, which is at the top of the ramp, and the final position, which is at the bottom. And here are the values. At the top, he's at a height of r, which is the radius of the circle. We're implicit in this, we have taken our coordinate system such that y equals 0 is at the bottom of the ramp. Plugging these values in, I can now solve for the speed at the bottom of the ramp. Putting in those numbers, I get 7.67 meters per second. For part B, we're going to have to use Newton's second law to calculate the normal force. At this point, he's still undergoing circular motion, and there's a gravitational force down, shown here in the free body diagram, and normal force up. And there's going to be a centripetal acceleration towards the center. But I know what that centripetal acceleration is because it's v squared over r. We've already calculated his speed. In fact, his speed is the square root of 2gr, so I can just put that expression in. So v squared is 2g over r. And so this acceleration is actually 2g, and it's upward. Now plugging this into the sum of the forces in the y direction for Newton's second law, I have n minus the work done, the gravitational weight is equal to 2mg. So that means the normal force is equal to 3 mg, which is 735 newtons. Finally, going back and looking at the solution, I note that his speed at the bottom of this ramp, which is the square root of 2gr, is exactly the speed he would have if he simply jumped off the side of the ramp and fell a distance r. And this ends example 7.4. In example 7.5, we're going to suppose that the ramp in example 7.4 is not frictionless, and that the skateboarder's speed at the bottom of the ramp is only 6 meters per second and not the 7.67 meters per second of the frictionless case. Given this information, we'd like to calculate the work done by friction in the problem. So if I look at the forces acting on the skateboarder at an arbitrary position, of course there's gravity straight down. As before, there's a normal force pointed towards the center of the circle, O, and there's friction pointed back, and this of course we'll assume is kinetic friction. If I look at a free body diagram of the motion, as shown here, the normal force again grows as the skateboarder reaches the bottom of the ramp, and this normal force, as the case before, that can't do any work because it points at a right angle to the trajectory of the motion. However, the friction force is pointed along the trajectory and actually is opposing the motion, so it will produce a work, and that work can be identified as W other in the conservation of energy equation. So to execute a solution, we'll identify some of the kinetic and potential energies at points of interest, in other words, at the initial position and the final position. So at point 1, the kinetic energy is 0, and at point 2, the potential energy is 0. At point 2, however, we do have kinetic energy because we're told that the skateboarder is moving at 6 meters per second, and he has a mass of 25 kilograms, and so the kinetic energy at that point is 450 joules. The potential energy at the top of the ramp is, as it was in the previous problem, it's simply mgh, and that's going to be 735 newtons, where the height is the radius of curvature, which is 3 meters. Now solving for W other in the conservation of energy equation, as shown, putting in the numbers, we get minus 285 joules. We note that this negative makes sense. The skateboarder is moving down to the right on this trajectory, but the friction force is pointing to the left, and so the work done by the friction must be negative. And this ends example 7.5. In example 7.14, a puck with coordinates x and y is acted on by a conservative force described by this potential energy function, where k is a constant. We'd like to find the corresponding force. Well, if you have the potential energy function, you can always find the force by taking the negative of its gradient. In particular, the x component is minus the partial u respect to x, and so forth for the y and the z components. Because this function doesn't depend upon z, the z component of the force will be 0, and the magnitude of the force is obtained in the usual fashion. So now we can calculate the two components of the force. The x component is minus kx, and the y component is minus ky. In unit vector notation, the force is minus k times this. The magnitude of the force is just k times the square root of x squared plus y squared, and I recognize that as the distance from the point xy to the origin. So I can write that as k times r. I can actually rewrite the force in this form, where r is simply a vector, position vector, corresponding to the point xy. And I note that u can be written as 1/2 k r squared, where r squared is x squared plus y squared. And I can now differentiate u respect to r with a minus sign, of course, and I get minus kr, which is what I have here. So as we found above, the force has a magnitude of kr, and actually the force points towards the origin because of this minus sign. And this ends example 7.14. In example 8.3, a soccer ball is kicked as shown in this diagram. The ball is initially moving to the left at 20 meters per second, and after it's kicked, it's moving up and to the right at an angle of 45 degrees with a speed of 30 meters per second. Given this information, we'd like to calculate the impulse on the ball and the average net force acting on the ball, where we're going to assume that the collision time is 0.01 seconds. So we're going to use the impulse momentum theorem to solve this problem, in which we got to relate the impulse to the average force acting on the ball. And since we're moving in 2 dimensions and these are vectors, we're going to need their x and y components. So the x component of the impulse is equal to the integral over the net force acting on the ball over time, but we're just going to take the average that to be the average force, and this is just the collision time, t2 minus t1. Of course, the definition of impulse is change in momentum, and here's the change in momentum in terms of m and v at the end of this equation. Likewise for the y component. Now we're in a position to put in the numbers. The angle is 45 degrees. So before the kick, we have an initial velocity purely in the minus x direction, 20 meters per second. And after the kick, there's both an x and y component of velocity, which is 21.2 meters per second. The mass of the ball is 0.4 kilograms. So it's an easy matter to get the impulse in each case, in each direction rather. So here's the impulse in the x direction, and here's the impulse in the y direction. The corresponding force is the impulse divided by the time, which is 0.01 seconds. So we get 1,650 newtons of force in the x direction applied by the foot of the soccer player, and 850 newtons of force in the y direction. The magnitude of that force is 1.9 times 10 to the 3 newtons. And the angle that the force is applied, taking the arctan of the y component of the x component, is 27 degrees. Notice that this 27 degrees is not the same as 45 degrees. So the angle of the force is not the same as the angle of the trajectory. We also notice that this force is really quite large, 1900 newtons. The weight of the ball, which is just m times g, is about 4 newtons. So gravity plays very little role in this change in momentum. And this ends example 8.3. In example 8.4, a marksman holds a 3-kilogram rifle loosely so it can be free to recoil. He fires a 5-gram bullet horizontally at a speed of 300 meters per second. Given this information, we'd like to calculate the recoil velocity of the rifle and the final momentum and kinetic energy of both the bullet and the rifle. So let's look at a schematic of the system. Here's the bullet rifle system before firing and after firing. So up here the bullet's inside the rifle, and we're going to take the positive x direction to be to the right. After firing, the bullet's expelled at 300 meters per second, and of course the rifle's going to recoil to the left. We're going to neglect gravity in this problem, and in fact assume that there are no external forces acting on the system, so that linear momentum is conserved in the x direction. The initial momentum of the system must be equal to the final momentum of the system, but of course before firing nothing's moving, so both of these have to be equal to 0. So 0 is equal to the final momentum, which is the mass of the bullet times the velocity of the bullet plus the mass of the rifle times the velocity of the rifle. Now it's a simple matter putting in the two masses to calculate the final velocity of the rifle, which is minus 5 meters per second. So it's to the left at a half a meter per second. Now we can calculate the final momentum and kinetic energies of everything in the system. So for the bullet, we get 1.5 kilograms meters per second, putting in the mass and its speed. Its kinetic energy, putting in the numbers, turns out to be 225 joules. The final momentum of the rifle, putting in the numbers, turns out to be minus 1.5 kilograms meters per second. Notice that this is equal and opposite to this, as it must be, because linear momentum is conserved. And finally, the kinetic energy of the bullet is 0.375 joules. We notice that the kinetic energy of the bullet is much, much higher than the kinetic energy of the rifle. And the reason that this occurred is that the rifle has a much larger mass than the bullet. And this ends example 8.4. In example 8.5, two gliders move toward each other on a frictionless air track and eventually collide as shown in this diagram. Initially, glider A is moving to the right at 2 meters per second and glider B to the left at 2 meters per second. And this is the positive x direction. Notice the gliders don't have the same mass. After the collision, they move apart, with glider B moving to the right at 2 meters per second. We'd like to calculate the final velocity of glider A. We'd like to look at how the changes in momentum and velocity compare for the system. So, since we're on a frictionless track, we're going to assume that the sum of the forces in the x direction are 0, so that the linear momentum in the x direction is conserved. So momentum before the collision is equal to the momentum after the collision, where the momentum consists of the momentum of glider A plus the momentum of glider B. So the initial momentum, since we have numbers for both gliders, is going to be 0.4 kilograms meters per second. We're going to set that equal to this final momentum and solve for the velocity of glider A after the collision, and we get minus 0.4 meters per second. Now we can look at the changes in momentum. So we'll begin with glider A. Its initial momentum is here. Its final momentum is here. We take the difference. We have numbers for everything. You get minus 1.2 kilograms meters per second. Doing the same for glider B, we get plus 1.2 kilograms meters per second. Notice that the change in momentum of A plus the change in momentum of B is going to give me 0. And that must be true because the momentum of the system can't change. However, this symmetry doesn't exist for the velocity because they don't have the same mass. So if I look at the change in velocities, A changed by a minus 2.4 meters per second, but B changed by a somewhat larger value of 4 meters per second. And the reason that the change in B is larger is that B has a smaller mass. During the collision, there's a force that's acting over a short time that's equal and opposite on both of them. They feel the same force but acting in different directions. But B has a smaller mass and it will therefore have a higher acceleration, and it picks up a bigger change in velocity. And this ends example 8.5. In example 8.10, we're going to repeat the air track collision of example 8.5. But now we have attached springs to the bumpers of the glider so the collision is elastic. Given the initial velocity of the gliders, we'd like to calculate the final velocity of the gliders, assuming an elastic collision. So let's look at a schematic of the collision process. Glider A is moving to the right at 2 meters per second, glider B to the left at 2 meters per second. And we're going to take this as the positive x direction. After the collision, they move apart, and we'd like to find these two final velocities, which we're going to call VA2 and VB2. We'll begin by using equation 8.27 that says that the relative velocities of the gliders before and after collision are equal in magnitude but different in sign. So here is the relative velocity of the gliders after collision, and that's equal to minus the relative velocity before collision. And of course, before collision I have the velocity, so I can put in the number. So I've got one equation. For the second equation, I'm going to demand that momentum is conserved, as shown here. And I can put in the numbers and organize it a little bit. And here's the second equation that involves VA2 and VB2. So my task now is to calculate these two velocities, given I have two equations and two unknowns. And of course I can do it by substitution. For instance, I could solve for VA2 in this equation and then plug it back into this equation and finally get VB2, and then go back stick VB2 into either equation to get VA2. In any case, here's the numbers that I obtained from solving those equations. And now I can evaluate my solution. One thing I'd like to verify is that the kinetic energy of the system remained unchanged. And it's easy to calculate the kinetic energy now. I'll call K2 after collision. It's going to be equal to 1/2 times 0.5, the mass of A, times the velocity of A squared, which is minus 1 squared, plus 1/2 0.3 for B times its velocity squared, which is 3 squared. And the answer I'll get is 1.6 joules, but this is in fact the kinetic energy that we calculated in example 8.5 before collision. So kinetic energy is indeed conserved, and this ends example 8.10. In example 9.3, a blue ray disk is moving with an initial angular velocity of 27.5 radians per second at t equals 0. However, it has a constant acceleration of minus 10 radians per second squared, as shown in this diagram. A line is drawn between points P and Q such that it lies on the positive x-axis at t equals 0. We'd like to find its angular velocity at t equal 0.3 seconds and the angle that this line makes at that time after it has rotated some. So we're going to look for this angle here, theta. This is clearly a rotational kinematics problem, and here's our toolkit for rotational kinematics, where we're going to assume that the angular acceleration is a constant. The angular velocity is given as a function of time with this equation, and here's the angular displacement as a function of time. And this equation relates the angular velocity to the displacement where time is not involved. So we're going to use a couple of these equations for the solution. Here's our parameters. The initial velocity is 27.5 radians per second. We'll take our initial angle as 0, and of course the angular acceleration is minus 10 radians per second squared. Plugging into this equation, we can find the angular velocity after 0.3 seconds has passed, and that's given here. For part B, we're going to use this equation, where theta naught, of course, is going to be 0. And this is the initial angular velocity, and here's the angular acceleration. And again, we put in 0.3 seconds into this equation. We find that's 7.8 radians, which corresponds to 1.24 revolutions. So basically, in 0.3 seconds, this line goes around one full revolution, and then about 1/4 more. So the line is pointed up somewhere here. And this ends example 9.3. In example 9.5, we're going to design an airplane propeller that's to turn at 2,400 revolutions per minute and to be fitted to an airplane whose forward airspeed is 75 meters per second. We're going to require that the speed of the tips of the propeller blades through the air not exceed 270 meters per second, which is about 80% of the speed of sound. So if we look at this diagram, we see that there are two motions in the problem. One is the circular motion with an associated tangential velocity, which is r omega, and the other is the motion of the plane, which is 75 meters per second. Notice that these two arrows are at a right angle to each other. We're going to calculate what the maximum possible propeller radius can be, and with this radius we're going to calculate the acceleration of the propeller tip. So let's look at a diagram of the motion. If we look from the front of the plane, we see at this moment that the tip of the propeller will be headed straight down at a speed v tan, which is simply going to be r times omega. And if I look at a side view at this moment, if the plane is moving out of the page at a speed of 75 meters per second, I also have a component of the velocity that is to the right. So these two velocity vectors are actually at a right angle to each other, so I can use the Pythagorean theorem to find the net velocity, which is this hypotenuse. The first thing I'm going to need to do is to convert the angular velocity of the propeller from revolutions per minute to radians per second. And here's the conversion factors, and I get 251 radians per second. Now I use Pythagorean's theorem. The tip speed squared must be equal to the speed of this plane squared plus the tangential speed of the propeller tip squared. And replacing this with r omega, I have this term. Now I can solve for r, where I'm going to replace the tip speed by its maximum value, which is 270 meters per second. As shown here, solving for r, I get about 1 meter. Now I can calculate the radial acceleration of the tip of the propeller with this radius. Putting in the numbers, I get 6.5 times 10 to the 4 meters per second squared. I note that this acceleration is 6,600 times greater than the acceleration of gravity near the surface of the Earth. So the internal stresses on the propeller tip are enormous, and this ends example 9.5. In example 9.6, we have an oddly shaped machine part as shown in this diagram. It consists of 3 discs, and these discs are connected to each other via massless rods of these dimensions. We're going to calculate the moment of inertia of this system about 2 axes. The first is an axis that goes through the center of disk A, such that the sense of rotation is around like this. And the second axis goes through the center of B and C. In that case, only A will be rotating around that axis. It'll be rotating like this. And finally, we're going to calculate the kinetic energy of the system for rotation about the axis through A at an angular velocity of 4 radians per second. We're going to treat these disks as point-like masses on the end of massless rods. And here's the formula we'll need. And these radii that are appearing in here are always the perpendicular distance to the axis of rotation. So for the first case, we have actually 2 objects that are rotating about this axis. There's this one, disk C, and its perpendicular distance is 0.4 meters. And the second one, of course, is disk B, and its perpendicular distance to the axis of rotation is 0.5 meters. Notice that the 0.3 meter dimension in the diagram doesn't play any role. Plugging in the values, I get 0.057 kilogram meters squared for that moment of inertia. The moment of inertia for this axis of rotation only involves one mass. It's A. That's the only one with a finite radius as it goes around. And its radius, of course, is 0.4. Putting in the numbers, I get 0.048. Now I can calculate the kinetic energy for that case, plugging in, for case A, plugging in that moment of inertia, and omega equal 4 radians per second, I get 0.46 joules. And finally, I note that rotation about A, since it really involves 2 masses, and one of them is actually quite far from the axis of rotation, gives me a somewhat bigger moment of inertia than the other case for this axis of rotation. And this ends example 9.6. In example 9.8, a light cable is wrapped around a solid cylinder with mass m and radius r. The cylinder rotates on a stationary horizontal axis, as we're going to show in this diagram. It rotates without friction, and there's a cable that's attached to a block of mass m held at distance h above the floor. The block is released and then subsequently falls. As it does so, the cable unwinds from the cylinder, forcing the cylinder into rotation. And we'd like to calculate the speed of the falling block and the angular speed of the cylinder as the block strikes the floor. In this problem, we're going to put our coordinate system down here. So we're going to measure the heights from the floor level. This is a classic conservation of energy problem where there's no forces doing work other than gravity. So the work done by other forces is equal to 0 in the problem, and hence mechanical energy is going to be conserved. So this is our initial position, and here's our final position in the motion. We start out with no kinetic energy, but a finite potential energy, which we're only going to assign to the block. The cylinder could have potential energy, but whatever it is, it doesn't change. The final potential energy in position 2 is going to be 0 because the block's at 0 height, that position. And the final kinetic energy consists of two terms. One's the translational kinetic energy of this block, and the other is rotational kinetic energy of the cylinder. We're going to treat the solid cylinder as a disk, and here's its moment of inertia. And we need a relationship between the speed of the block and the rotation rate of the cylinder. We note that points on the perimeter of the cylinder move with a speed that's equal to r times omega. So we can solve for omega in this equation and plug it into the kinetic energy equation. So here's our conservation of energy equation, of course, with W other equal to 0. Putting in the terms and making this substitution where omega becomes V over R, we end up with this expression collecting terms, and we can now solve for V. We note that this speed has a couple of interesting limits. In the limit where the mass m of the cylinder gets very, very large, this whole speed is going to go to 0. So if this were an extremely massive cylinder with a very light block, the block would float down very slowly, and so it would not take up much velocity before it hit the floor. In the opposite limit, where the mass of the cylinder is equal to 0, this term goes to 0, and we find that V would just be equal to the square root of 2gh, and in fact the block would hit the floor at a speed as if it were simply dropped from a height h. And this ends example 9.8. In example 9.9, we're going to use the parallel axis theorem to calculate the moment of inertia of this mechanical linkage about an axis that goes through its center of mass as shown. We're given the moment of inertia about a parallel axis that goes to the end of the linkage here. So we'll call this I center of mass for this axis and IP for the parallel axis. They're separated by 0.15 meters. The equation we'll need is equation 9.19 as shown, where m is the total mass of the linkage and d is the separation. Solving for ICM, we get this value. Finally, we note that this center of mass moment of inertia is significantly less than the moment of inertia at the end. And this is always true. The center of mass moment of inertia is the smallest. And this ends example 9.9. Example 9.10. A hollow cylinder of uniform radius ρ with length L is shown in this diagram. It has an inner radius R1, which defines the hole, and an outer radius R2. We'd like to use integration to find its moment of inertia about this axis here, so we can think of the cylinder as rotating as such. To do this, we're going to have to choose a differential volume element over which to carry the integration. A natural one for this geometry is a cylindrical shell of length L and radius R, where R is arbitrary. We'll take its thickness to be dr. And I note that the area of the shell will be its circumference, which is 2 pi r times its length L, and the volume is this area times the dr. The nice thing about the shell is every element of the shell is an equal distance from the axis of rotation. Now we can calculate the moment of inertia as the integral of r squared dm. dm, of course, is obtained by simply multiplying this differential volume element times the density. Putting in the volume element into this equation, we get this, and we can pull the constants out in front. So we just have to integrate over r cubed, and we get this expression. We can simplify this a little bit and get rid of the rho by factoring it as such, and then identifying the volume of the hollow cylinder. That volume is going to be equal to the volume of a solid cylinder minus the volume of the hole. So the first term is the volume of the solid cylinder, the second term is the volume of the hole. The mass of the cylinder is obtained simply by multiplying by rho, and I compare this expression with the terms here And I make the identification that the moment of inertia can be written as 1/2 m times r1 squared plus r2 squared. Now I can evaluate this expression in a couple of different limits. The first one is to take r1 equal to 0, and in that limit the moment of inertia will simply be equal to 1/2 m r2 squared, and that's the familiar moment of inertia of a disk. The other limit is where r1 is just a little bit less, about equal to r2. So now the entire thing is a cylindrical shell, and in this limit I will be about equal to 1/2 times m times 2 times r2 squared. Since r1 and r2 are about equal, and that 1/2 cancels the 2, and so this will be about equal to m r2 squared. And that's the familiar moment of inertia of a cylindrical shell. And this ends example 9.10.